Hey everyone, how's it going? Today we're going to solve this really neat related rates problem that I found. And it goes something like this. We have a cylinder that is partially filled with some fluid. We're just going to say it's water. Water is a typical incompressible fluid. It's filled partially with fluid, and the cylinder has a radius of big R. At the same time, we have a cone of a circular cone, radius r and height h, being lowered into the cylinder at a rate of 1 centimeter per second. And the question is, once we submerge the cone fully into the cylinder, what is the rate of change of the height of the fluid? And I think a good way to start this problem is to imagine the cone partially submerged in the cylinder. My drawing's a little bit off scale, but let's imagine that we have this sort of scenario here. We know that the rate of change at any given time of the fluid in the cylinder, and I'm going to call the volume of the fluid in the cylinder big V with this line across it, that rate of change must equal the rate of change of the submerged volume of the cone, which I'm going to write as little v. So little v is submerged cone volume. Okay, so we need to find expressions of the volume for both the cylinder and also the submerged part of the cone. Really easy for the cylinder. For the cylinder, it is going to be just pi times big R squared, and it's going to be h as a function of time here, the height of the cylinder fluid as a function of time. We don't quite know what it is, but let's just leave it as h of t for now. Now for the submerged part of the cone, the radius and the height are changing over time. So at any given time, let's look at a cross section of the circular cone here, and let's just choose a random spot of fluid. So let's say that the fluid line is right here at some given time. We know that the height at that point is y, and the radius is x. So if we were to write the volume of the submerged part of the cone, that is equal to a third, since that's a circular cone, times pi x squared y. Both x and y are functions of time, because as you submerge the cone, the radius changes and the height changes. So this is not going to make it very easy for us because we got two variables here. But the really cool thing about this is we can actually write one in terms of the other, because these are actually, we can kind of make a similar triangle equivalence here, where the big triangle here is h and the big radius is r. So now I can go ahead and write, I'm going to write x in terms of y, because the y part, the height part, is what we already know, that it changes at a rate of 1 centimeter per second. So that is going to be x over y is equal to r over h. So x is equal to r over hy. And now I could go ahead and write the volume of the submerged cone as 1/3 pi, and I'm just going to skip some steps and do some simplification here. R squared over h squared times y is y cubed. Alright, so we got both of the parts that we need to solve for the rate of change of the height. 3 parts, actually. I'm going to go ahead and put them all together right here on the side. Okay, so I went ahead and condensed the 3 main equations right here on the left-hand side. This is y as a function of t cubed. And let's go ahead and solve for the derivatives of each respective volume of the cone, the submerged part of the cone, and also the volume of the fluid in the cylinder. So the rate of change of the volume in the cylinder is equal to pi r squared dH dt, and that's because the radius stays constant and the only thing that's changing is the height of the fluid in the cylinder. Okay, now let's go ahead and do the same for the volume of the submerged part of the cone. That's going to be dV dt is equal to 1/3 pi r squared over h squared. All these are constants, and we're just going to take the derivative of y as a function of time. That's going to be 3, and I'm just going to omit the of t part here, dy dt, due to chain rule. And this here cancels out, and we can go ahead and tidy this up by writing this as pi r squared over h squared y squared dy dt. Okay, so there's a few key things here. We actually already know what dy dt is. We know that that's equal to 1 centimeter per second. That's given at the beginning of the problem. So I'm going to go ahead and rewrite this as this here. And the very last thing we're going to do is we're going to evaluate this derivative at y equals h, because we're fully submerged in the fluid in the cylinder. And that's going to be equal to pi r squared over h squared times h squared. So that's just going to simplify down to pi r squared. Alright, now all we have to do now is to go ahead and equate this rate of change of volume to this rate of change. And that's going to be pi big R squared dH dt is equal to pi little r squared. And here, let's go ahead and solve for dH dt. dH dt, divide pi r big R squared on both sides. We're going to get pi little r squared over pi big R squared. That's just equal to r squared over r squared. Units are going to be distance over time, so that's going to be centimeters per second. And that's going to be it. That is the solution to this problem. I really like this one because there were a lot of moving parts in this problem here, and really gets you thinking. really has you try different things until you finally find the right solution to this. But let me know in the comments what you think of this. Did you enjoy this video? Hit the like button if you did. Subscribe for more, and I'll see you guys next time. Have a good day.